Fluid mechanics is a branch of physics that deals with the study of fluids, which include both liquids and gases. It encompasses the principles and laws governing the behavior of fluids at rest, fluid statics, and in motion, fluid dynamics. Fluid dynamics, specifically, focuses on the study of fluid motion, including the forces and energy transfers associated with it. It involves the analysis of fluid flow patterns, velocity distributions, pressure variations, and other characteristics of fluid motion. Key concepts and principles in fluid mechanics and fluid dynamics include continuum assumption. It assumes that fluids can be treated as continuous substances rather than discrete collections of molecules. This assumption is valid as long as the fluid being studied contains a large number of molecules. Conservation laws. These laws are fundamental in fluid mechanics and are based on the principles of conservation of mass, momentum, and energy. They provide the basis for analyzing fluid behavior and solving fluid flow problems. Fluid statics. It deals with the equilibrium conditions of fluids at rest, focusing on the distribution of pressure in a fluid. Key concepts in fluid statics include hydrostatic pressure, buoyancy, and Pascal's law. Fluid dynamics. This branch examines fluid motion, including the study of fluid flow patterns, forces acting on fluids, and the relationship between pressure, velocity, and cross-sectional area. It involves analyzing both laminar, smooth, and turbulent, chaotic, flow regimes. Bernoulli's principle. This principle states that in an ideal fluid flowing along a streamline, the total energy, sum of pressure, kinetic energy, and potential energy per unit volume, remains constant. It is commonly used to explain the lift generated by an airplane wing and the flow of fluids through pipes. Reynolds number. It is a dimensionless parameter used to characterize the type of flow, laminar or turbulent, based on the ratio of inertial forces to viscous forces in a fluid. The critical Reynolds number for the transition between laminar and turbulent flow depends on the geometry and flow conditions. Navier-Stokes equations. These are a set of partial differential equations that describe the motion of fluid substances. They provide a mathematical framework for analyzing fluid flow, but their solutions are often challenging and require simplifying assumptions for practical applications. Fluid mechanics and fluid dynamics find applications in various fields, including engineering, e.g., designing efficient pipes, pumps, and turbines, environmental science, e.g., modeling water and air pollution dispersion, meteorology, e.g., predicting weather patterns, and aerospace, e.g., studying aerodynamics of aircraft and rockets.